right, we have an interesting one here where we're looking at a physical pendulum and a simple pendulum and we're comparing their periods. So we have two pendulums shown in the figure below. I drew them up on the board. Each consists of a uniform solid ball of mass m supported by a rigid massless rod. But the ball for pendulum A is very tiny, so that is our point mass, or our simple pendulum. And the one for B is much larger. Find the period for each pendulum. Which one takes longer? Okay, so to start with, we need to figure out the period for both of them. So we're going to start with this equation and we're going to find the torque produced by gravity. So mg times the sine of theta times how far away that force is acting from the axis of rotation, in this case L. I do need to put a negative sign on there to indicate that it's opposite the displacement, which we're going to get a theta here in a second for. So because it's a small angle, the sine of theta is approximately theta. Again, we're trying to get into this format. That's why we got to get rid of the sine. All right, so now I have negative mg times L, I'll divide the I over as well, times theta is equal to alpha. This then is my omega squared value. So next, to get the period, I just have to take 2 pi divided by that omega. So we will have to inverse this in order to put it into our period equation. So period is going to be 2 pi times the square root of the inverse of this, so I divided by mgl. Do the same thing for our physical pendulum. So period is equal to 2 pi times the square root of I divided by mgl. We will have to do a little extra work over here to find the moment of inertia than we do on this side. So because this is just a point mass, this is just going to be mr squared, where r is the distance from my point mass to my axis of rotation. In our case, that's L. So we get 2 pi times the square root of ml squared divided by mgl. All right, so the m's cancel, one of the l's cancels, and our period is going to be 2 pi times the square root of L over g. Now we come over to this one, and we want to figure out how different is it than that. Okay, so we come over here to find the moment of inertia. We are going to need the parallel axis theorem. So the moment of inertia about d is equal to the moment of inertia about the center of mass plus m times the distance between the two squared. In our case, it's going to be L between the center of mass and our new one. The center of mass for a moment of inertia of a solid sphere, I'm going to look that up on my table. And so I see that as 2/5 mr squared, and in our case, r is L over 2 squared plus ml squared. Now I just need to add these together. So let's bring this out. So I get 1/4. And so I do 1/4 times 2/5 gives me 1/10. 1/10 ml squared plus ml squared gives me 11/10 or 1.1 ml squared. So you can already see that the moment of inertia is not terribly different, about 10% different. So let's see how that plays out now. So I have period is equal to 2 pi times the square root of 1.1 ml squared divided by mgl. Again, our masses cancel, one of the l's cancels, and we're left with that 1.1 inside the square root. So I'm going to bring that outside of the square root here. So I get t is equal to about 1.05 times 2 pi times the square root of L over g. This part here being equal to the period for the simple pendulum. So it's going to be a little bit slower by about 5%. So in using that, we have about a 5% slower period than if it's just considered a point mass, which is pretty amazing considering the size of this physical pendulum relative to that axis of rotation to center of mass distance. So you can assume a lot of things are simple pendulums just based on that kind of an error. There you go.